Hey. So, I'm going to talk about trains today. So I found this lovely train image from the past. So web transport today and tomorrow in half an hour. So this is me, as you heard. I do curl quite a lot. I actually wrote my first HTTP implementation basically 20 years ago. I've been doing HTTP since I participated in IETF with HTTP 1.1, HTTP 2, and with Quick now since about 10 years back, and I'm employed by Mozilla. So, web transport is HTTP. So, of course, HTTP is more than web. HTTP is used by a lot of other services today too, but I'm going to focus on the web side of things here, because the web is sort of what the users see, and this is what's going to run through your networks a lot going forward. We started out with HTTP 1 back in the 90s. 99 was the last invention of HTTP 1.1. It has been with us for a long time. We shipped HTTP 2 roughly 2 years ago, and we're going to see something else which isn't HTTP 3, but it's Quick. And I'm going to run through this for you. If we look a little bit on some of the trends on the web today, looking at the major websites out in the world, we can see that there's a definite trend. We're going up in volume and up in number of objects over the years. An average site now has more than 100 objects these days. All those objects need a HTTP request one by one to get them, and the amount of data is increasing quite a lot too. And there's no stopping in this trend. It's got to continue like this for more time. What is notable then is that on average there are more than 50 resources of these for each site that reside on the same domain. I'll explain why that matters. HTTP 1.1 is what I call a round-trip bonanza. It is this ping-pong thing, you know, request and response. That's me and the cloud, right? And the cloud is far away in many instances. There's a long time waiting. I'm sending a request, I'm waiting for the response to come back. Sure, I can open more connections, but each connection has this ping, pong, and that's many hundred milliseconds, sometimes longer than that, sometimes shorter. So we're waiting for the response to come back, and then we send the next request and response, and the next request and response. Once upon a time, we thought we could solve this in HTTP 1.1, and we introduced pipelining, which means that you can send multiple requests before any response comes back, but that sort of was never deployed. It didn't really work, so we don't use that in any desktop browser today. This is what we do. We send a request, we wait, we get the response back. We send the next request. That's not a very good use of TCP, as you can see. So, we introduce another problem then with that we call head-of-line blocking. Since we then open more connections to handle this, instead of waiting on one connection, we open more connections. We have more lines in the supermarket. So when you, as a browser, want to send out a request, which line is the fastest, right? When you stand there in line in the supermarket, which line is the fastest? Really hard to tell, right? It's never the one you pick. Sure, TCP-wise, you can always sort of start your own new line, in theory at least, but there's a limit to that too, and there's a penalty for that in resource and time and so on. So a tricky problem for browsers today. Two of the problems with HTTP 1.1 that, of course, crafty people in the world have sort of invented funny workarounds. So there's a long time to the cloud to get back. Ping pong, we have to wait. So instead of doing that a lot of times, why not put all images into one, right? 178 flags in one image. This is not ping pong, ping pong, ping pong. This is one. Bing, bong, a lot of flags. And of course, you only want to show 3 of these on each page, but sure, you saved a lot of round trips. It's really bad for your cache, and you got a lot more data than you wanted, but it's faster. Or you just cram it into the style sheet, like this. It's not very friendly to anyone who's reading this, but this is then, you ask for a style sheet, but you don't only get the style sheet, you get a lot of icons or images embedded in the style sheet. Ask for the style sheet, get a whole bunch of stuff back. Saves round trips. You get a lot of data. Or if you're using JavaScript, get all the JavaScripts at once, right? Because, same sort of spirit. Ask for one thing, get a whole busload back. Saves round trips. We open connections to each host name when we're surfing the web, right? Web browsers open 6 TCP connections per host name. Simplified speaking, but that's basically what we do. So when you want to have more than 6 connections to your website, you just create some new host names for your website, and wham, you have more connections. So if you have a lot of images on your website, some sites do, you just create more host names and you get more connections. This doesn't really scale, and it's really tricky for the browser then to sort of keep all these connections alive, especially when you sort of move around on the site. Which connections are you going to keep alive and which do you have to close? You can't really keep 100 connections for each site alive for very long. So yeah, that works. But to sort of mitigate some of those problems and bring in those workarounds, in sort of stop having them as funny workarounds, hacks on HTTP 1, we started working and we shipped HTTP 2 in May 2015. And with HTTP 2, we tried to create protocol primitives to do the same things that were workarounds, but now they're defining the protocols how to do that. So for example, I should emphasize this then, that we changed how we send HTTP, but we don't change HTTP. HTTP is the same thing, we just change how we transport HTTP. So we still have request responses, we have headers, we have cookies, we have everything you love about HTTP, but we just send them differently. So, for example, then, we made HTTP 2 multiplex, so we can have one connection, and we can send several different streams over that single connection. Like in this case, we have one image of a Justin train, and we have one image of an IKEA train. And you want to get them over an HTTP connection, you split them up into frames, and you send it over one connection, frame from different streams on the same connection, multiplexed. Justin and IKEA trains in one connection. That is sort of one of the core primitives of HTTP 2 that made it possible to now suddenly we don't need to open all those connections. We can actually send a lot of resources over the same connection, much better in many cases. And this then makes it a lot better. It is using a TCP much better now. So instead of doing this, that's me and the cloud. And instead of, I'm sending a request and I'm getting a response back. But instead of waiting for that response coming back until we send another request, we can send the other request at once. We don't have to wait. We can just fill the outgoing pipe immediately, request. And it'll send responses back when it has time for it. And in this case, might be one of the requests might be slower, so it might actually sort of end after this second request. We can sort of utilize TCP much better. We can fill the pipe in both directions much better. And we can do these sort of basically unlimited number of streams over the same physical connection. Great. That is what we shipped with HTTP 2. It's now out there, live on the internet, and not that many people noticed, actually. The transition and the deployment of HTTP 2 has been really smooth and sort of painless for most people. Basically, all servers that you care about support HTTP 2 today. They've been doing it for a long time too. These are basically a bunch of the open source ones and a bunch of the big commercial ones. So a huge portion of all the server softwares speak HTTP2 since years back, and all the browsers do, also since way before we even shipped the RFC. So we have the servers, we have the browsers, and now we only need the users to use these things in the right combination, right? So if we're looking at the in Firefox that I work with, we collect, or people can opt in to sort of agree to send in user statistics. So we can actually see how large percentage of all the traffic that is HTTP2. And Firefox statistics of April this year, 35% of all HTTP is actually HTTP2. So I'm talking about HTTP as a concept and not as a protocol, and HTTP2 is a protocol. And this is based on the volume of HTTP. And as you may remember from reading about HTTP2 before, all the browsers, and in fact all the servers too, there's really no deployment in the world that actually speaks HTTP without HTTPS. So this is the total per HTTP, which means that as a share of HTTPS, and HTTPS is the requirement for HTTP2. So out of HTTPS on the world today, 70% of the servers that Firefox users talk to are responding HTTP2. A question there? Sorry, once? Number of connections or traffic volume? This is number of connections, a number of HTTP requests done by Firefox users who are participating in this data. So it's heavily skewed to early users and to mass volume sites. So of course, this means that all the big, Google, Facebook, Twitter, and some others are a big portion of this. And of course, the long tail is not a big factor here. So that taken into account, I think 70% is still a large number. If we look at it from the other end, we can see that if we're just scanning the top 10 million sites in the world, 13% of them run HTTP2, and that has doubled the last year, which I think is fairly good, still sort of far away from even half of the servers in the world. Looking at the top 1,000, we're approaching 1/3. And of course, if you deploy it on your site, or I deploy this on my site, so I have 90% of my visitors using HTTP2. That might not be true for everyone. You may not get exactly 90%, but all the browsers support this, so most of your users will go HTTP2 if you just let them. So that was sort of HTTP1, the problems, and then we did HTTP2. HTTP2 had some new fun things, and then we deployed it, and a lot of users are using it. So what did we sort of get out of that 2 years down the road? Was it good? Did anyone sort of get happy with that? Some did, some did not. This is numbers, also again measured from Firefox. From the really remote corners of the internet, we should look at the bottom of this table. Round trip times to the site you're communicating with, the 95th percentile of Firefox users. They're roughly a second away. That's a long time. Request, response, 1 second. And of course, if you're waiting for each response to come back before you send the next request, that is a lot of time. Watching a regular website in this situation, that's painful. Going HTTP2 here is making things a lot better for these users. We're gathering queuing time in a Firefox. That means sort of when Firefox, the browser, wants to send a request to the site you're browsing, it puts the outgoing request in a queue to wait until it gets sent over the wire to get the request. That's the queue. It sits in the queue, and then it gets sent out over the network. So we can see then how the queuing time has changed from HTTP1 to HTTP2. Of course, sitting in the queue, a shorter time is a better situation. Here we can certainly see that for the worst cases, 2 seconds waiting time, down to 16 milliseconds time, on average in the 95th percentile. Again, this is the really remote corners of the internet where you're probably on some really, really lousy wireless networks. But still, this is a huge improvement to those users. We can also see then that the percentage of requests that are sitting in the queue for longer than 100 milliseconds, that's the number in the bottom, sort of has drastically decreased. So, if you're having a really shitty internet, H2 is really, really the solution for making things better, or at least according to some metrics. Here's another metric. Here's a fun, this is a slide I've stolen from Fastly. Human made an excellent presentation. You should Google if you want to see more specifics about this. But he's basically measured how H1 and H2, HTTP1 and HTTP2, compares with Firefox and Chrome in different network situations. And we don't have to care about the details here properly, but we can see if we're looking at speeds here, we can see that the blue line and the red line, the blue and orange is Firefox, red and green are Chrome. Blue and red are faster than the other ones. H2 wins in the 0% packet loss situation. That's sort of the key from this slide. 40 millisecond latency. So this just shows that, yeah, if things are good, fairly decent latency, no packet loss, H2 makes your sites faster. 2% packet loss, not so good anymore. 2% packet loss, of course, is an awful lot of packet loss. So that's not your typical Wi-Fi or whatever, it's a really broken Wi-Fi. But it still shows you that, wham, suddenly H1 is much better than H2 for both browsers, and by quite a margin too. Not a good situation, or as I would put it, a sad face. This is clearly the worst case for H2. And this is where one of the reasons to start looking at why is this? Well, we have one connection instead of 6. Packet loss for one connection, of course, that hits that one connection and all the streams. It's not just 1 out of 6, it's 1 out of 1. It has to sit there waiting. That makes it a header line blocking, so one packet loss means everything waits for that packet to sort of get resent, reappear. With a 2% packet loss rate, that's a lot of waiting for a lot of streams, possibly 100 streams or more. So as you remember, we have this is sort of TCP IP, and there's a TLS, and there's a H2 on that, and there's a train. Well, there are 2 trains, the Justin train and the IKEA train, right? And when we lose a packet somewhere here, they're not aligned, right? When we lose a packet somewhere, everything has to wait so that we can repair the streams or the connection, and we can go on with the trains. Not really what we want in a 2% packet loss situation. So we want to fix the TCP header line blocking. Right, how hard can that be? Someone did this. Well, a non-blocking TCP TLS HTTP2 implementation, right, with independent packets. So each packet that you lose, they have to sort of be stream aware so that you can lose one packet and the other streams can continue. You don't have to wait for that particular packet you lose, right? But you can't do that with TCP because it's a stream, it's not packet-based, you can't do that. So we need something to sort of do that, re-implement it. Maybe we should do a new TCP or change TCP. Well, you know, as good as I know that we don't deploy new protocols. And we don't do new transport protocols because TCP and UDP are basically the only protocols we can deploy today. So basically that's sort of out of the debate. So we're making a new protocol instead on top of another protocol like UDP. Fixing TCP or changing TCP, that could be done, but it's a sort of a very, very slow process that is take ages or decades or whatever. TCP fast open is an excellent example of a change that takes forever to actually get deployed in the wild, or if it is even doable. So doing this in the real world today is called QUIC. QUIC is a protocol that is implemented and deployed widely by Google. It is basically what I said. It is a TCP-like thing with crypto and H2 frames over UDP. And the entire thing in user space, in the browser and in the server. It is using end-to-end crypto. It doesn't reveal much of the actual underlying things to anyone who want to interfere with it. So with this, you don't get any TCP head of line blocking. You actually get independent streams that are actually, you can lose a bunch of packets in one stream and the other streams can go on. Changing things on this in this layer also introduces new fun things that you can introduce zero RTT connections. You can actually start a new connection without any round trip sort of ways to the handshake time to get a new connection. You get a zero RTT if you had a previous connection with the server. But it sort of fixes a lot of other, you can, when here, you can fix a lot of other sort of issues you get with TLS and TCP. And it makes it a busload of, magnitudes faster. If you happen to be a global company with a huge market share, you can just fix client side and server side at the same time and iterate really, really fast. And yeah, it works. Google QUIC is today 7% of the internet data traffic. Now. If you're using Chrome now, you're using QUIC already. It works. Again, QUIC maintains, is also sort of like H2. It maintains HTTP semantics, same things, request, response, headers, everything, just changes how it is transported. So instead of being disaligned, it is aligned. Losing just the Justin car, the IKEA train can continue. So the Google QUIC is now converted into the IETF, or taken into the IETF, and there's becoming an IETF QUIC. So it is going to become a standard, and this is going to become something that we're going to see deployed from more companies than just Google really soon. Maybe in mid this year. There's going to be an interop draft in June, hopefully. So this is not HTTP 3 in anything, in any name at least, but it's basically what it's going to become. And it's not TCP 2 either, even if some of us thinks of it that way. It's just QUIC. And that's the official logo for QUIC. That's what I wanted to tell you about. Thank you.
Okay, do we... We have 3 or 4 minutes if there's time for just a couple of quick questions. Quick questions being the British terminology. Can we have the microphone over here, please?
Hi, Christian Larsson from Deutsche Telekom. So, are we done now, or are there more things to fix? Will there be a QUIC 2 or an HTTP form, whatever you might want to call it?
Given how we came to this point, I would say that no, we're not done. But I don't think anyone is looking past QUIC, and QUIC isn't really done in any way or fashion either. The Google QUIC is being changed quite a lot in the IETF, so we're not really sure what the IETF QUIC is going to be. And sending H2 over QUIC is just the beginning of QUIC. QUIC is going to be used to send other transport protocols too. So I think QUIC is the beginning of something that is going to go on for a longer time, and it's going to be much more than just H2.
Okay, so I'm also curious about the changes that are going in. I mean, you mentioned here you had Google QUIC, and you're saying IETF QUIC. What are the, I mean, from a very high level perspective, kind of, are there technical improvements, or is
there's a lot of changes. I mean, if you want to get 150 emails every day, subscribe to that GitHub repo. It's an insane activity. But for example, the Google QUIC has its own crypto, and the IETF QUIC has TLS 1.3. That's a huge differentiator. And there's a lot of discussions changing every single packet headers, negotiation. Yes, I don't think there's a single bit that remains the same in that one as in that one. They're both called QUIC, so they're sort of hard to differentiate that way, but there's going to be a lot of polish and tweaking to get sort of Google's mindset sort of converted into how it should be as a standard.
Okay, is it a quick question? Yeah. Can you wait for the microphone? Sorry.
quick question?
Yeah, there's room for a lot of good puns or bad puns.
No, but is there follow-up on that? Are there any major conceptual differences between the Google QUIC and the IETF QUIC? No.
The major conceptual differences is that the Google QUIC was made to send H2 only. It's an H2, they sort of squished all the layers into one. We send H2 over UDP, magic happens. But when they took it into the IETF, they did that under the condition that, no, we're going to do this for more than H2. So now the conceptual difference is now that it's sort of split up now into a transport layer and sort of an application layer within QUIC. So you can send H2 over the transport QUIC. So you should potentially send DNS over QUIC or whatever over QUIC transport.
So IETF QUIC is turning into TCP, new TCP over UDP.
It is turning into TCP and a transport layer above it, yes, and TLS. I think I'm out of time.
Yeah, I think is it a very speedy question? Okay.
Quick, quick.
As I understand, QUIC it's mem from Netnod. As I understand, QUIC is on top of UDP. Is there any thoughts of having it just on IP directly, to have it as a third protocol or so over IP?
Well, no, because that's sort of all the NASA firewalls are saying no. So they're just stop, don't do that. So no.
Okay, I'm sure Daniel will be around to answer more questions, but for now, can you thank him for a great presentation? Thanks very much, Daniel.
Thank you.